Hi everybody, this is Mrs. Westmoreland, and today's lecture is about oxidation-reduction reactions. So in the last unit we talked about two types of reactions that occur in solutions, the precipitation reaction and the acid-base neutralization reaction. Well, another main category of reactions that occurs when you have an aqueous solution is called an oxidation-reduction reaction, and these are reactions that involve electron transfer. And so actually the synthesis and decomposition and single replacement and combustion categories of reactions could fall under the umbrella term of oxidation-reduction reaction because they all do involve electron transfer. So the first thing we need to do for oxidation-reduction reactions is we need to learn some rules for assigning oxidation states. And oxidation states are sometimes the same as what we think of as an ionic charge. So if it's an ionic compound, it generally is the same as the charge on the ion. But we can also assign oxidation states for covalently bonded substances. And here, oxidation state is more like the assigned charge on an atom. And it's really just a number that's used for electronic bookkeeping. So for keeping track of where the electrons are being transferred from and to in an oxidation-reduction reaction. So there's a set of rules that are listed here in the notes, and I'm really just going to go straight to the exercise to determine the oxidation states in the compounds. So you'll notice that in exercise 16, all three of those examples are covalently bonded. They are two nonmetals. So in A and B we have neutral molecules of covalently bonded substances, carbon dioxide and sulfur hexafluoride. And in letter C we have a polyatomic ion. So within the polyatomic ion, the nitrogen and the oxygen are sharing electrons. And then that whole cluster of atoms has a charge which could then participate in ionic bonding. So usually at least one of the rules from the rules for assigning oxidation states applies, and then you can use that information and number 6 of the rules, that the sum of the oxidation states must be 0 for an electrically neutral compound, and for a polyatomic ion the sum of the oxidation states must equal the charge of the ion, to figure out what the other atoms are. So one of the atoms that almost always has the same oxidation state is oxygen, which is -2 in almost all compounds, unless it is in peroxide or if it's paired up with a more electronegative atom, which would be fluorine, the only one on the periodic table that would be more electronegativity. So we can pretty safely assume that oxygen is going to be -2 no matter what. And so I immediately went and I assigned oxygen -2 in the CO2 and oxygen -2 in the NO3-. The other one I found is fluorine, which is always assigned an oxidation state of -1. So that's also its ionic charge, and because it's the most electronegative atom on the periodic table, it's always going to be -1. So in sulfur hexafluoride, fluorine is -1. So now once we know one of the atoms, then we can apply rule number 6 about adding up the oxidation states to be 0 to figure out what the carbon is. So since there are two oxygens in carbon dioxide and each one has an oxidation state of -2, then that -4 plus whatever the oxidation state of carbon is needs to add up to be equal to 0. So therefore the carbon's oxidation state in that particular compound is +4. So also, since we assigned an oxidation state of -1 for fluorine, and there are 6 fluorines in sulfur hexafluoride, then 6 times -1, which is a -6, plus whatever the oxidation state of sulfur is, has to add up to be equal to 0, so the sulfur is +6. And then since nitrate is a polyatomic ion, instead of being adding up to 0, we add it up to equal the charge on the polyatomic ion. So the 3 times the -2 of the oxygen plus whatever the nitrogen is needs to add up to -1. So the nitrogen needs to have an oxidation state of +5. So this does not mean that nitrogen has lost 5 electrons. It does not mean that it is in an ionic bond with oxygen. It still is sharing electrons with oxygen. This is just its assigned state, which helps us keep track of oxidation and reduction reactions. So the next thing we generally do in oxidation-reduction reactions is we identify which atoms are what are known as oxidized and which atoms are reduced in a particular chemical reaction. And so we can do that by looking at an acronym where we have oil rig, or Leo goes GER is our mnemonic device here, where oxidation is loss of electrons. That's how you get oil. You could also say losing electrons is oxidation for Leo. And reduction is gain of electrons. That's where you get the rig, or gaining electrons is reduction for GER. So anytime you have a loss of electrons or an increase in oxidation state, or a gain of electrons or a decrease in oxidation state, that's the way we're going to tell when oxidation and reduction has occurred. So in exercise 17, I have written in the oxidation states of the atoms for the reactants and the products. So in the reactants we have the metal aluminum the element in its elemental state. So any element has an oxidation state of 0. And then we also have solid diatomic iodine, which is the elemental state of iodine. And so therefore the I in I2 also has an oxidation state of 0. Then when they're in the ionic compound, aluminum iodide, their oxidation state is the same as their ionic charge. So we have a metal and a nonmetal. Aluminum is +3, iodine in group 17 is -1. And so you can see that the aluminum has changed from an oxidation state of 0 in the reactants to an oxidation state of +3 in the products. So you can think of it as losing electrons, forming the ionic compound, or you can think of it as increasing in oxidation state. And so therefore we say that the aluminum has been oxidized. We also say that the aluminum is the reducing agent, because by giving up its electrons, it has given them to iodine, so it has caused the reduction of iodine. So whatever is oxidized is also the reducing agent, and conversely whatever is reduced is also the oxidizing agent. And there will always be one of each in an oxidation-reduction reaction. So the iodine changes in oxidation state from 0 in the reactants to -1 in the products. So it has decreased and gained electrons. So that is reduced. And therefore the solid iodine is also called the oxidizing agent. Here's another one where it is a little more complicated, because it's not just elemental reactants. But essentially I've just gone through and I've assigned oxidation states for each of the atoms in the reactants and products. So since lead sulfide is an ionic compound, I know that the sulfur from group 16 has a -2 charge, so the lead has to be +2 to balance that out. O2, oxygen gas, is the elemental form of oxygen, so it's 0. Also applying the ionic charges for the lead oxide in the product, and then using that assigned charge that oxygen is nearly always -2, and if it's -2 and there are 2 of them, then the sulfur in the SO2 has to be +4 to balance that out and add up to 0. So then I'm looking for the changes, and I can see that the sulfur has changed from -2 to +4. So I say sulfur, the atom sulfur, has been oxidized. But I say the compound in which I find the sulfur on the reactant side is the reducing agent. So the lead 2 sulfide is the reducing agent. Then I also see that the oxygen has changed from 0 to -2, so the oxygen has been reduced, and again it's the compound or the molecule that I find the O in on the reactant side that is called the oxidizing agent. So it is individual atoms that are either oxidized or reduced, but it is reactants that are called the oxidizing agent or the reducing agent. Also, in the second equation, I've done the same thing, and again, I'm looking for those atoms that change in oxidation state. So going down in oxidation state from +2 to 0 for the lead is reduced, and going up from +2 to +4 for the carbon is oxidized. So the lead atom is reduced, the carbon atom is oxidized, so the reactant that contains lead 2 oxide, is the oxidizing agent, and the reactant that contains carbon, the carbon monoxide, is the reducing agent. So the third thing we're going to do, and this is just going to be an introduction, is the balancing of reactions by the half reaction method. So redox reactions are generally net ionic reactions. They omit spectator ions, and they need to be balanced not only for number of atoms, but also for charge, also for number of electrons transferred. So when I have a skeleton equation, like I do in this first sample problem, the first thing I do, according to the rules, is I divide the equations into an oxidation and reduction half reaction. So essentially, I just split up into two parts. The permanganate ion changing into manganese, and I could see that this is a +7 permanganate turning into a +2, so that's the reduction half reaction. And the iron 2+ changing into the iron 3+ is the oxidation half reaction. So first I just split those two halves of the reaction apart. Then I balance any atoms other than oxygen or hydrogen, and in this case I don't have any of those. So I have one manganese and one manganese in the first equation, and one iron in the second equation. So I don't need to balance the atoms that are not oxygen or hydrogen. So when I need to balance oxygen, as I do in the first half equation, I need to add water to balance the oxygen. So since these occur in aqueous solution, I can always add water to the side that does not have as much oxygen in order to balance oxygen. I also add hydrogen to the opposite side, H+, because many of these occur in acidic solution, and that then allows me to balance out the hydrogens that I've added. Finally, I add electrons to bring the overall charge down to equal the charge of the smaller charge. So you can see in this case we have 8 H pluses plus permanganate, which is -1, for an overall charge of 7+ on the reactant side. And we have 2+ manganese and neutral water for an overall charge of 2+ on the product side. So I need 5 electrons to be added to bring the more positive charge down to equal the more negative charge. Here I have 3+ on the product side and 2+ on the reactant side, so I need to add 1 electron to get those two charges to equal. Then finally, before I add the two equations back together, I can multiply through by whole numbers so that the total electrons gained is equal to the total electrons lost. So since I have 5 electrons on the reactants here, I need 5 electrons on the products here, and I multiply the whole equation through by 5. Then I add the two half equations together and cancel out the common terms, which in this case is the electrons, to get an overall equation of this. And when I go back and I double check to see that it's balanced for atoms and charge, I see 8 hydrogens on the reactants and products, 1 manganese on the reactants and products, 4 oxygens on the reactants and products, 5 irons on the reactants and products, and an overall charge of 17+ on each side. Thanks for listening. See you in class.